Welcome back, friends. Okay, so we have been looking at uh, the rest frame solutions of the Dirac equation essentially. So we looked at in the limit where the particle is at rest, and then of course we can always boost it by applying a corresponding Lorentz transformation on these things. Okay, I'll come to the Lorentz transformations and how to apply Lorentz transformations on Dirac equation in the coming lectures essentially. But just to get an idea, we will just wanted to write down the solutions of the Dirac equation, and they can be solved easily from here. Okay, from this particular thing we can always take the rest frame solutions in which p bar is equal to 0 essentially, or the derivative of the x and y and z are set to 0, and you can easily solve this equation essentially. As we see that this equation has solutions of this particular type, very easily we can see, which is psi bar of this is the again a matrix equation essentially. This is a 4 component form essentially. This is 4 times 1 and this is also 4 component times 1 essentially, and each of this component has this property that it is 1 0 0 0 0 1 0 0 0 0 1 0, and this is the 4th component essentially here. And what we see is that the first 2 components have positive energy solutions and the second 2 quantities are negative energy solutions. And so in the last class what we have said is that we cannot escape negative energy solutions, and I also mentioned the comment that compared to Klein-Gordon equation, Dirac equation solutions have a positive norm, meaning what I meant was essentially that the probability density, or if you want to interpret a probability density or derive a continuity equation from the Dirac equation in the same form as what we have seen essentially, that in terms of psi bar psi or psi dagger psi or something essentially, psi star psi essentially. Okay, this has a positive norm. I did not explain how to calculate that norm, neither I said it, but I said it always has a positive norm, and so this, but even with a positive norm you cannot escape negative energy solutions essentially. Now before doing that, before going to computation of the probability density and stuff like that essentially, let us try to see what could be a Lorentz scalar essentially. It will turn out to be, what could turn out to be a Lorentz scalar in with this wave function psi. So the wave function we started is psi essentially, psi 1, psi 2, psi 3, psi 4. So this is a column vector essentially in the gamma matrices vector space, which I have mentioned it essentially. Now if you take psi dagger psi, you would expect, okay, this is a scalar, but it turns out this is not a Lorentz scalar essentially. What you will have is essentially psi 1 square plus psi 2 square plus psi 3 square plus psi 4 square. And as we will see later on essentially, as we will see, for the present let us take it as a result essentially, and we will see it later on. This is not a Lorentz scalar. Now you may ask me the question, why this is, again go back to the why this is not a Lorentz scalar, because you know that, okay, these are 4 different solutions in general, they are not Lorentz scalars essentially. This is not a Lorentz scalar. Now there is a homework problem associated why this is not a homework Lorentz scalar also, but we will also do how to do so we will start maybe a bit later in this class or a bit later How to do Lorentz transformations on Dirac spinors? We will start doing it. Before that, we also will start doing what are the what do you call what are Lorentz transformations, what are the groups associated with Lorentz transformations, and so on. So, but for the present, let us just take the results that the psi dagger psi is not a Lorentz transformation, but instead what is the Lorentz what is the quantity which is Lorentz scalar. So, this is not a Lorentz invariant quantity. So, if you want to define probability, you need to define a Lorentz scalar. Okay. So, this Lorentz scalar is psi bar psi. So, psi bar where psi bar is equal to psi dagger gamma 0. So, let us do what it is essentially. Psi bar is equal to psi dagger gamma 0. So, that is equal to psi 1 star, psi 2 star, psi 3 star, psi 4 star whole into gamma 0, which is nothing but beta, okay, which is nothing but beta, which is 1 0 0 0 0 1 0 0 minus 1 0 0 0 0 minus 1, then into psi 1. Now you can calculate this is quantity essentially. So, it gives you a minus sign on the other 2 points. So, if you want, we can calculate psi bar psi is equal to, so this gives me psi bar psi is equal to psi 1 psi 2 psi 3 psi 4. So, this is mod psi 1 square plus mod psi 2 square mod psi 3 square minus mod psi 4 square, and this is a Lorentz invariant quantity. So, this is a, we will see why this happens essentially, that this is a Lorentz scalar. Now, later on we will see how to construct which are Lorentz invariant quantities, which are called something called bilinear covariants. For the present, we use this definition essentially with psi bar is equal to psi dagger gamma 0 to to derive, which is always positive definite essentially. So, which is always positive definite, turns out to be positive definite essentially. Now, if you see, now what is the current associated, just to introduce the current essentially, it turns out that you can start with the Dirac equation. Let me write it down in the same fashion. So, you write the current essentially. So, you can multiply the current, okay, J mu, and the continuity equation, okay, probability continuity equation. J mu equal to psi bar gamma mu psi. This is a vector, it's a 4 vector Lorentz index. So, this is a Lorentz 4 vector, okay. This is a Lorentz 4 vector, and the probability current density conservation is given by this relation essentially, where J mu contains as usual rho and J bar, probability current and probability current density, and psi bar rho is equal to gamma 0 psi, that is equal to psi bar gamma 0 psi, that is equal to psi dagger psi. This is the covariant, essentially the definition of this thing. So, in terms of now you may say that I have not achieved anything by writing in this particular fashion, but this will give me the Lorentz covariance essentially. Okay, it is always positive definite, essentially it is always positive definite. Okay, for both positive energy and negative energy particles essentially. Solutions. Okay, so it has always a positive definite norm. So you can always say J is equal to J0 is equal to rho and integral rho d cube of x is equal to integral psi dagger psi of d cube of x, which is always positive definite. Now the important thing why this is because now why this is important is because it does not contain any because of the gamma 0. So del mu J0, if you look at the difference between the current equation of the Klein-Gordon field and the current equation of the Dirac field, now you see that there are no double derivatives of the probability density. So there are no double derivatives of the probability density, it is always linear single derivative So you can never, it is the continuity equation of the probability density is always positive definite essentially. So these are the what do you call advantages of the Dirac equation, but it does not tell you that why they should be positive definite essentially, why they should I am sorry why should they so it is always positive, but it does not escape you. Okay. So it makes sure that both negative energy solutions and positive energy solutions will always have positive norm, but there is no way of escaping negative energy solutions essentially. Okay. This is the reason why this is the case essentially, that okay, this is the case that you have there is no way of escaping negative energy solution from the Dirac equation. Now let me digress a bit, because I mentioned that what are these things, what are these wave functions, what are, I am saying that okay, I need to tell you how to they transform on the Lorentz transformations, okay, and how to construct Lorentz spinors and what are these spinors and everything, what is this wave function, okay. Now what are these different aspects essentially, okay, of okay, why this is why something is not Lorentz invariant, why something is Lorentz transformations and everything essentially. So the reason is that we have to go a little bit what is the space and everything. This is comes under something called so this is something called the Lorentz transformation group, and we will try to explain what this Dirac equation has to do with Lorentz equations as Lorentz transformations. So before doing that, I would like to introduce a little bit more about the Lorentz transformations essentially. So what are spinors? Now I introduced you, there are these two quantity, I introduced you that the upper two components are called positive energy solutions. So I introduced you a quantity called psi. What are these solutions? And the upper two components have positive energy solutions. And the lower two have negative energy solutions. So let me, and now from from rest frame, I can always, one can always apply Lorentz transformations on rest frame solutions and get solutions at any moment. But before doing that, a little bit more we need to understand what these are called essentially. So okay, why these are what is the relation between this spinor space and Lorentz transformations essentially. So psi I can replace before, okay, in terms of u of xt, v of xt, this is positive energy spinor, this is negative energy spinor. I said spinors are essentially vector spaces, vectors in vector spaces spanned by gamma matrices. So this is what I said essentially. Before doing that, the spinors can come in very, the smallest spinor you can have is in dimension 2. So the upper two components have the same energy as a positive energy. So essentially I call them as positive energy spinor. I call it as U spinor, essentially I call it as a U spinor. The lower two components have negative energy, so they are called as V spinor essentially. So U spinors of the Dirac equation are called positive energy spinors, V is the negative energy spinors. Now U contains two components only, and this is also a two components. So spinors typically come under 2, 4, 6, 8 and so on. So depending upon the kind of dimension of space we are considering and the the Lorentz transformation, and this we are considering essentially. For 4-dimensional spaces, essentially for 4-dimensional spaces, we have Lorentz transformations 4 dimensions. Okay. So, the spinors can be either 2 component or 4 component essentially. Now, to understand, okay, I'll make this statement, but to understand you require a little bit more background about the Lorentz transformations and something called the representations of Lorentz group essentially. Okay, representations of Lorentz group and Poincare group essentially. This is extremely important to understand what spinors are essentially and what is their relation with the Lorentz group. So, in 4 dimensions, this I mean 4 space time dimensions essentially. So, you have x mu essentially, and mu is equal to 0, 1, 2, 3. So, we have only 4 space time dimensions. In this case, spinors can be 2 dimensions or 4 dimensions. So, when I say spinors, I mean Dirac spinors. I will explain I'll explain in more detail in the coming lectures, but spinors are much more generic mathematical objects essentially, much more. So, what I mean by Dirac spinors here is means solution representations of Lorentz group. So, the representations of the Lorentz group can be now can be either 2 dimensions or 4 dimensions. So, these are 2 dimensional means when I mean 2 component essentially, each dimension corresponds to 2 component spinor or 4 component spinor. Now, I want you to distinguish between the number of space time dimensions and the number of say spinorial dimensions. They have no there is a relation, but they are not in general equivalent to each other essentially. So, for example, if you have some spaces in is equal to so so let us just say, so okay, just give you a picture which we will also do it essentially, a number of space time dimensions. This is extremely important exercise, so that you distinguish between space time dimensions and number of gamma matrices. Now, we started with the relativistic equation essentially in 4 dimensions. So, E square is equal to px square plus py square plus pz square plus m square essentially. Okay. So, the starting point is always this essentially. So, okay. Okay. So, the starting point essentially, let me write it down here, E is equal to alpha I pi. Okay, I can remove the arrow essentially, plus beta m, and this will give me gamma nu is equal to 2 g mu nu. Now, let us say that I want to start with this essentially. So, I am starting with this. So, number of alpha linearly independent alpha and beta required essentially. Suppose I am in 1 plus 1 dimensions. okay, I am in 1 plus 1 dimensions of space time. That means I only have, there is no x and y direction essentially there. So, the 2 dimensional space essentially. So, the gamma matrices I have are only 2, they are only 2 which are essentially the sigma matrices. Okay. Okay. Now, if you have so I have 1 x and 1 time, 1 space time, 1 space direction and 1 time direction. I only have 2 gamma matrices which are your sigma matrices, which are your this thing essentially. So, if we have 1 plus 2 which is 3 dimensional space, it remains the same essentially, it remains the same. Now, if we have 4 dimensional space, which is essentially what we are dealing with, the number of gamma matrices you have is 4. If you have 5 dimensions, so if there is some extra dimension x, y, z, z prime or something, essentially the dimension of the gamma matrices is essentially 5, essentially 4 itself, it remains 4, but there are other issues essentially and everything. So, if you have 6 dimensions, you have 8. So, you see the dimension of the Dirac-Spinor in 4 and 5 dimensions is 4, but it has not, it is not really a correlation, it just happens that there is a correlation here, but it does not mean that this Spinor dimension is 2. That means you can explain the entire physics in terms of 2 component dimension, 2 component spinors essentially. The Dirac equation has solutions in terms of 2 component dimensions. Now, how do I see this? Now, you go back to again your E is equal to alpha pi plus beta m. So, if alpha is number of alphas, so p I is equal to 1 and 2, okay. In the first case essentially I is equal to 1 and 2, there are 1 alpha 2 alpha and beta, only alpha and beta are required. In the first case there is only 1 alpha and 1 beta, so there are only 2 matrices which are required. In the second case also, even if there are 2 alpha matrices, it turns out the solution is only 2 alpha matrices are linearly independent. So, that is sufficient to explain all the Dirac equation in 1 plus 2 dimensions. This is extremely important for us to understand condensed matter physics essentially, applications in condensed matter physics. Okay. Now, again next go to 4 dimensions. We have seen alphas are essentially alpha 1, alpha 2, alpha 3 and beta, and we found that there are only 4 linear, we need 4 linearly independent matrices which are your Spinor indices, which set your Spinor index dimension is 4. Now, if you go to 5 dimensions, that means let us say there is a hypothetical, okay. So, this is hypothetical spaces. These are not physical spaces, but some hypothetical unphysical spaces if they exist essentially for hypothetical reasons, okay. For some reasons they may exist essentially, and this has implications for theories with quantum gravity and so on. So, you need 4 alpha matrices and 1 beta matrix, but it turns out in 4 dimension there are only 4 independent of them with you cannot have solution, you can only have solutions with 4 dimensions essentially, 4 dimensional mass alpha matrices essentially. So, you have 4 alpha matrices and 1 beta matrix, and all the 5 can be found out in 4 dimensions of the alpha matrices essentially, and the dimension of the Spinor is still 4. Now, you raise the dimensions to 1 more. So, if you have 6 dimensions, the number of alpha matrices is 5 and one beta matrix. So, there are 6 linearly independent matrices. So, if you want to find 6 linearly independent matrices, it is only possible with dimension 8 matrices. It is only possible with dimension 8 matrices, and so the dimension of the spinor is 8. And there are other reasons also which will come later on. Essentially, the Dirac matrix is actually a bit special, essentially Dirac spinor. And so, if you want Dirac spinors, essentially you end up having this kind of conditions, essentially this kind of conditions. So, we will so what we see is that what we have seen is that the spinors, okay, to define spinors, the dimension of the spinors is just sort of accidental, that it has the same dimensions as the space-time dimensions in 4 dimensions, but it can also exist in lower dimensions. In fact, as we will see, for massless particles, essentially the solutions are essentially when m is equal to 0, the solutions are only u and v, essentially. So, that means you only have there are only there are different kind of classes of solutions in which there are only 2 component spinors, essentially. But to understand the spinors a little bit more, I will introduce a little bit of group theory and what is the representations, what are spinors, and why it should never be confused with the space-time Lorentz index. Okay. I had to introduce some background in group theory, which I will start doing in the next lecture. Okay. Okay. Thank you very much, essentially, and for listening to me. So, we will start looking at a little bit of group theory and what is the Lorentz group and what is called a group representation, and then we will come back again to understanding the Dirac equation here, essentially. Okay. So, thank you very much, and let me stop here.